This is John Mellor-Crummey. In this talk, I'm going to give a brief overview of sampling-based performance analysis with HPCToolkit. I'll begin my talk by briefly introducing sampling-based call path profiling. Then I'll describe how to use HPCToolkit to collect performance data for an application on a single node. Then I'll demonstrate data collection and profile analysis using the approach I just described. Next, I'll demo trace analysis on some larger data for a 256 rank MPI execution. And I'll finish up by providing some pointers to some additional information about measurement. Sampling-based performance monitoring periodically interrupts each thread in an application. Interrupts are triggered by a sample source as a metric reaches some predetermined threshold. For example, we might set a timer to interrupt each thread every thousandth of a second. Or we could set up hardware counters. For instance, we could count every time 5 million instructions have completed, or we could get an interrupt every time 1 million cache misses have occurred. So why would we use sampling for performance measurement? Well, first, it has control overhead. We can set the sampling rate low, and then the measurement will have low overhead. And second, sampling avoids blind spots. It's going to measure everywhere, no matter whether you're in the application or whether you're in dynamic libraries that it's loaded, and it minimizes systematic error by making sure that we have measurements everywhere. HPCToolkit uses sampling to attribute metrics to call paths. When a thread's timer or hardware counter reaches some predetermined threshold T, we interrupt the thread and we unwind its call stack. We take the interrupt at some instruction as shown in red, and then we might be inside some routine C when called from B, when called from A, when called from main. And so this represents a calling context. This is called a call path sample, and we'll take whatever the threshold T is and we'll attribute to this path. So we'll charge T to the thread's current calling context. And then over time, what we'll end up building is a calling context tree of all of the contexts that occur in the application. And the tree will accumulate weights in each of the nodes that represent the costs that were incurred in particular calling contexts. So the overhead for collecting these call path samples is proportional to the sampling frequency and not the call frequency. And so by dialing down the sampling frequency, we can get low overhead. This slide outlines how to use HPCToolkit to measure a sequential or multi-threaded application on a single node system. First, use HPC run with no arguments to launch your application MyApp. This will profile the CPU time of your application and deposit the results in HPCToolkit MyApp measurements, a directory. The next step is use HPC struct to analyze the MyApp measurements directory. This will analyze the application binary and all dynamically loaded libraries that appeared in the address space as the application executed. In the third step, we'll use HPCProf to analyze the measurement data that was collected with HPC run and use the program structure information recovered by HPC struct to do so. This will create a database directory that we'll then look at with HPC viewer. Now let's apply the simple recipe that I just described to measure the LULESH application from Lawrence Livermore National Labs. So we'll start with an empty directory here. And first thing I'll do is I'm going to use my command history to accelerate my typing. So I'm going to git clone a copy of LULESH. We'll cd to the LULESH directory, and then I'll run cmake to build the make files for it. And so what I'm doing here is I'm going to be compiling using the G++ compiler. I'm compiling for OpenMP only, so MPI is turned off. And I'm compiling it rel with debug info. That means that the compiler should perform optimization, but also record line map information that relates the machine code back to the source code. So now that I've got make files, I'm going to build the application. And then next, I'm going to run the application under the OpenMP runtime system. So the machine that I'm running on has two 24-core processors, 96 hardware threads total, and I'm going to run a small example on just 8 threads. So I'm going to specify OMP num threads is equal to 8, and I'm going to use HPC run to run Lulesh 2.0. And there's a couple of arguments telling it a relatively large data size and a relatively short number of iterations so that it completes fairly quickly. And so using HPC run, it ran in 13.91 seconds. And so if I look in the directory, now I have a measurements directory that's recorded. So let's just try running this without HPC run and see how long it takes Lulesh without HPC run. So you get an idea of the measurement overhead for HPCToolkit. So HPCToolkit, it ran in 13.91 seconds. So let's see how long it runs without HPCToolkit. Ran in 13.80 seconds. So you can see that the measurement overhead was on the order of 0.11 seconds. Pretty small. All right, so now we have our measurement data. So now let's use HPC struct to analyze the binaries in the measurement directory. So some of the binaries in here belong to the application. Some of them are binaries that our tool brought into the address space of the application. HPC struct is just analyzing all of them because it's simplest to do that and it's fast. So I mentioned that this system has 96 hardware threads on it. And so by default, when I apply HPC struct to a measurement directory, it is going to do the analysis of the binaries in parallel using half the number of threads that are available on the machine. So in this case, it used 48 threads. And since the binaries were small, it's actually analyzing them concurrently, using one thread to analyze each of the binaries and launching concurrent analysis. If the binaries were somewhat larger, if they're over 100 megabytes, then in fact, it would apply 16 threads to analyze the large binaries to accelerate that. So now we have our program structure information. So now we use HPCProf to compute the analysis results by combining the measurement data with the program structure information. That was quick. And now finally, we can use HPC Viewer to view the measurement data. So when the user interface comes up, we can see that there are two categories of things shown in the top-down view. It says program root and thread root. Program root refers to everything that is reachable by the main thread. And so in this case, you can see that 1/8 of the time was spent inside the main thread and 7/8 of the time was spent inside the OpenMP helper threads. So there's the top-down view here, there's a bottom-up view and a flat view. So let's look at the flat view first. The flat view can tell us, I'm looking here at exclusive time. That tells me where we actually spent time in the application. And what this says is that 80.6% of the time was spent in the Lulesh application itself. 15.9% of the time was spent in this library with a long path name. So this is libgomp in a path that came from SPAC. So we were using GCC 11.2. And we spent small amounts of time in libc and libm, so just 2.6 and 1%. So if the application were running really well, we would have spent almost all of the time in Lulesh, but here we have a fair amount of time in the OpenMP runtime library. And so that means that 15.9% of the time we're spending inside the OpenMP runtime library rather than actually performing computation in the program. So this really counts as overhead. So that's a sign that this program is not running very efficiently. Now let's go back to the top-down view. So if I select program root, we'll first look in the main thread and see what's in here. So I'm going to select the flame button, and this shows me a deep call path. And so inside the function main, there's a loop at line 2745. And inside that loop at line 2748, there's a call to Lagrange leapfrog. Now, this here's the name of the routine that we're calling, and this is listed as being inline code. And so I can get to the call site by clicking on the number, and I can get to the callee by clicking on the name over here. And so this takes us into Lagrange leapfrog. And now if you notice, the routine is only a few lines long, and it took us to the first line where it found executable machine code, which happens to be the call site for another inline function, Lagrange nodal. So that happens to be line 2609, where Lagrange nodal is called. And then Lagrange nodal at line 1235 calls calc forces for nodes. So we see that there's a long chain of inline functions. All of these inline functions, the information about that was recovered from the application binary by HPC struct. And then finally, we see that on line 782, it's invoking a parallel region. And so we can see the GNU runtime is now invoking the parallel region. And so the code inside the parallel region came from inside this function, calc hourglass force for elements. And so inside the function, there's a call to the parallel region. And then the OpenMP compiler split out the code for the parallel region from this function, and it just gives it the same name. And you notice on the right-hand side, it says clone.omp_fn0. And so that's the outline function created by the compiler. And so then we can see then further down the call chain that inside the function that there's loops and other inline code as well. And so what we have here is a detailed picture of the call chain. Now, if we move to the bottom up view, and again, I'm going to sort by exclusive time. Exclusive time is the time that's spent just in a function. Inclusive time is the time spent in a function and things it calls. And so in the bottom up view, if I sort by exclusive time, then that's going to tell me where I spent the most time in the application. And it says 14.7% of the time is spent in do spin. Well, that doesn't sound very productive. So let's see where do spin came from. So now this is showing me a set of either real procedures or inline procedures. And so in this case, we treat the inline procedures as if they were real procedures. And now I can use the flame button to look up call chains and find out where do spin was called from. And so I can see that do spin was called from do wait, which was called from team barrier end, which was called from gomp thread start, so which is called from thread root. So this means that a worker thread is sitting inside a barrier waiting for work and spin waiting. And so that means that the threads are spending some time spin waiting, looking for work. So in the profile views we've looked at so far, the time dimension is compressed out. All of the samples have been aggregated together into a calling context tree. So how could we get some understanding of what's going on in an execution over time? Well, one idea is to take all of these samples we're taking n times a second, and we're going to organize the samples for each thread or MPI rank along a timeline. And then we'll view how the execution evolves over time. And then what do we view? Well, we're going to assign each procedure a color, and then we're going to view a depth slice of the execution. So the gray plane shown on the screen represents a visibility plane. If we lift it all the way up to the top and then just show the top slice, what we would see is that everybody is in the blue routine, which represents something like me. And then if we move down one level of abstraction down to the green level, then maybe that's some sort of run procedure. If we move down one level more, then we start to see more information being revealed about what's happening inside the run procedure. Perhaps it calls an initialization phase represented by the yellow, followed by some solve phase represented in the purple. In the time I have remaining, I'd like to give a brief demo of HPCToolkit's trace view. So traces are more interesting for larger executions. And so rather than demoing the trace with 8 threads worth of Lulesh, I'm demoing here using 256 MPI ranks for a code called Flash from the University of Chicago, which is simulating a white dwarf detonation. So let's move from the profile view to the trace view. So in the trace view, we have along the left edge, you see this alternating set of colors. And so the height of the bar indicates the height of a trace line. And so each of these little bars represents an MPI rank. And so I can find out what particular rank I'm looking at by using this little ruler on the left. So we have all of the processes are each assigned a row, and then we have time is flowing from left to right. This simulation ran for 542 seconds. There is a cursor in the middle of the display, and at the cursor, which is on rank 128, 271 seconds into the execution, this is showing the complete call path. And so this comes from our call path unwinding. Now, in the bottom pane, what it's showing us is a history of the call stacks for thread 128. For the thread that the cursor is selected, it's showing us what the call stacks look like at various points in its execution. Now, when we're rendering this view, everything is sampled because we may not have enough horizontal or vertical pixels to display all of the points that we have in time. Now, what we're showing in this top view is we are at level 0, and so the color blue indicates that all of the threads for the entire execution are either in flash or things flash called. And so this is a top-down hierarchical view. And what we see is for the entire execution, everybody is executing within the program flash. There's a couple of little flecks in here, and these are for call stacks that didn't properly unwind. Those are called partial unwinds, but they're not worth our attention since there are so few of them. So now this is at depth 0. We're looking at the top where everybody's in flash. So let me move down one level, and I can do that by just selecting in the call stack here. Now, if I move down one level, what I find is that this thread is in a call to driver evolve flash, and that's represented by the green color shown here in the legend and also shown on the screen. If I want to see the call stack over here, I can just click at any point, and that's going to show me that the call stack is for rank 144 at 47 seconds into the execution. And here's the call stack, and the red color corresponds to driver init flash. So it's important to note that these colors are not a legend for the display. These are colors that represent each of the procedures in the call stack, and each of the procedures is assigned its own unique color. And so this procedure, this magenta procedure, happens to be in the call stack at depth 1. And if I want to see this grid expand domain, which is underneath it in the call stack, I can move down 2 levels, and now this is going to turn brown, showing me that it's showing the grid expand domain. So what we see is at the second level, we see there's an init flash phase followed by an evolve flash phase. We can move down one more level in the call stack, and now we see additional structures. So in fact, the initialization phase is separated into 2 halves. There's init source terms and init domain. And I can see that just by clicking on these, clicking on the colors and seeing what the corresponding functions are. Then we can see that the evolution is a series of bands that repeat. So this is an iterative code. And every so often we see that there's something different that happens. We can find out what that is by clicking on it. This says grid update refinement. Okay, so now I'm just going to move down a couple of levels in the call stack to see if we can find anything interesting. So one thing that jumps out on us is, in fact, we see that there's some imbalance over here. So if we're expecting the program was SPMD and everybody's spending the same amount of time in this particular phase of the code, we see that some of the processes are taking longer. And then there's this purple color. And so let's find out what this purple is. So in fact, this is an all reduce. So what's happening is we can't begin the next phase until there's an all reduce that completes, and the all reduce can't complete until the lagging processors finish this phase. So there's a little bit of load imbalance in this phase. So if we move down a couple more levels to see if there's any interesting structure that's revealed, well, in fact, we find that there's even more load imbalance in here. In fact, there's a fair bit of load imbalance inside these phases. And so some of the processors are spending substantially longer in this simulation init block than others. And in the meantime, everybody else is waiting in this phase that's grid, refine, derefine, and they're in a barrier waiting for the lagging threads to show up. So let's go back to the home view. So right now I'm zoomed in on this particular area, and the mini map shows the area that I'm zoomed in the trace. I'll move back to the home view, which shows everything. I'm going to move down another level or so, and I'll zoom in on a couple of iterations and see if there's anything that's of interest. Well, one thing we can see is that there's a sharp vertical edge in the middle of this. And generally, these sharp vertical edges indicate that there's some kind of collective communication. So if I click and see what the green is, so I see this is in flux conservation, but actually underneath it's calling an all reduce. And so I can move down to the level at which the all reduce is happening. So the purple here represents an all reduce. So there's some imbalance in this. There are some of the processes are waiting in the all reduce for others to show up, and then some show up at the last instant, and that's when the all reduce is able to complete. Now, so there's an imbalance of waiting in the all reduce, but that doesn't have to do with imbalance in the computation phase before it. It looks like everybody's spending about the same amount of time in the computation phase before it. However, in a preceding phase, we can see that there's some load imbalance here, that some of the processes are spending time in this AMR 1 block CC prolong gen UNC fun. So this is some sort of prolongation step where some of the ranks are participating and other ranks do nothing. And the ranks that do nothing, they arrive in the reduction very early. So I hope this gives you a sense of how to approach the trace view. You start from the top and you move your way down and you look at the highest level of abstraction that that can shed some insight. And you can look for load imbalances and serialization and things like that. In the presentation thus far, I've described how to use HPCToolkit to collect performance data for a single-threaded application or a multi-threaded application running on a single node. In the slides, there's also some information about how to use HPCToolkit in conjunction with a job launcher to collect performance data across multiple nodes. In addition, there's some information about specifying sample sources. The default sample source is CPU time. There's also a real-time sample source. And there's also some detail about how to use hardware performance counters. One of the important things when you're collecting measurement data is to control the measurement frequency. The recommended way to do it is automatic, to use the default frequencies that HPCToolkit provides. You can also have explicit control, and using the Linux perf events measurement subsystem, you can use either frequency-based sampling or period-based sampling. I encourage you to consult the slides for these additional details.